A metal wire of mass, okay, is allowed to slide without friction on two horizontal rails. Okay, so when they say metal here, what they mean is conductor. It conducts electricity. On two horizontal rails, spaced a distance d apart. Okay, see figure. Okay, I'll add in a little d. There we go. The track lies in a vertical uniform magnetic field B, which is going to be perpendicular to the track. Constant current I flows from a generator along one rail across the wire and back down the other rail. Oh, they say with mass, just so that we assume it has mass, therefore when it's accelerated it doesn't infinite acceleration. Okay. Find the velocity, speed, of the rails, I'm going to assume natural rails, as a function of time, assuming it to be at rest t equals 0. Okay, so first thing I'm going to do is I'm going to redraw this picture. Not because the picture is wrong, it's just, I don't like it. Yep, don't enjoy that picture. I feel aggrieved and affronted by that picture. Not a big deal, just I do. Alright, so then we're going to have a rail like this. So this is our rail, and we're going to have a current going through. I'm going to say this way. And this is going to be some battery, but we don't really care about the voltage because it's told that we don't have a constant voltage, we have a constant current, which is convenient. And therefore, there's going to be a force equals QV cross B through this. So backtrack, kind of the concept we have going on here is current is charge flowing through a conductor. In reality, it's negative charges flowing in the negative direction. By convention, we're assuming that positive charges are flowing in the positive direction. So this current's going this way, this has positive charges moving down this way. So if we say we have a magnetic field going into the board, yeah, that probably works fine. Magnetic field going into the board. They just tell us it's perpendicular. They don't tell us up or down. So if we do the right hand rule, V cross B, so we point our fingers in the direction of the first vector. In this case, the first vector is V. Cross it by B, which is into the board. We're going to have a force going that way. So this is going to create a force going this way. If we did it backwards, it'd still work. It doesn't tell us if the bar is going towards the generator or away from. Doesn't matter. That's not the point. The point is that it's going to be moving. And so the other way, another way of writing this equation, this is not going to be a proof by any means, just sort of a feels. Looking at velocity as dimensional analysis, so we're going to say it's measured in distance over time, meters per second. We're going to take this per second and we're going to move it from the velocity over to the q. So this gives us q per, I'm going to say q per time times distance cross b. Well, charge per unit time, that's the exact concept of current. So we actually have the other formula, which I'm going to write as IL cross B. Force equals IL cross B. So force is the current times the length of the wire cross the magnetic field. Magnetic field is into the board. The length of this wire is perpendicular to it. Cross product is a measure of how perpendicular two vectors are. So this is going to be the same. So the magnitude of the force is going to be ILB. Now, when we learned this in the Navy, the mnemonic we used was fire incinerates little bunnies. I know it's kind of juvenile. That's the way the Navy works, at least with its mnemonics. And it works. At least the mnemonic works. F equals ILB. So now, from this point, I'm going to say that force can also be defined as mass times acceleration. Therefore, we can get the acceleration out of this, and we can say that acceleration equals current, length of the bar, magnetic field, over mass. And all of these are constant. So what we're told what this gives us is that we have a constant acceleration, and as soon as you hear a constant acceleration, you're like, oh, kinematic equations. So kinematic equations are A equals A, V equals AT plus V naught, just for completion, X equals 1/2 AT squared plus V naught T plus X naught. And this is just integrating the constant acceleration. And then another equation I'd like to write up is velocity final squared equals velocity initial squared plus 2a delta x. And that's not really a new equation, it's just a combination of the other two. But we don't have to go through all that because it asks us for the speed, which just is going to use this equation. So we're going to say that velocity without a little vector arrow, meaning that it's velocity without concern for the direction, i.e. speed. It's going to be the acceleration, ILB, which I'm going to write the L as D because they tell us that the distance between the rails is D, which in this case is the same as L, over mass times T. And then V naught goes to 0 because they tell us the initial velocity is 0. And so that's all we have to do for this problem. Make sure we got everything we need. Velocity, current. Yep, uniform magnetic field, constant. Yep. So they give us all those pieces of data. The only thing that would throw me here is I wrote dB, and this is distance, not to be confused with the derivative b, nor decibels. So that's how I'd approach this problem. Hope it helped. See you in the next one.